Picture this. You're standing in a dusty workshop behind a farmhouse in rural Iowa, surrounded by rusted engine parts, scattered tools, and the smell of motor oil mixed with fresh hay. The sound of cicadas fills the summer air, and in the distance you can see endless rows of corn swaying in the breeze. Now imagine that in this seemingly ordinary setting, a 16-year-old girl with grease under her fingernails and determination in her eyes is putting the finishing touches on a machine that will revolutionize agriculture worldwide and leave Tesla's engineers scrambling to catch up. This is the extraordinary story of Emma Johnson, a high school junior from a small farming community who built an electric tractor so advanced that it didn't just compete with Tesla's upcoming agricultural vehicles, it completely outperformed them. Using nothing but salvaged parts, online tutorials, and an intuitive understanding of both farming needs and electric engineering that amazed industry experts, Emma created a breakthrough that major corporations had spent millions trying to achieve. But how does a teenager with no formal engineering training, working in a barn with limited resources, develop technology that eluded teams of PhD engineers at one of the world's most innovative companies? How does someone who should be worried about prom dates and college applications instead find herself fielding calls from Fortune 500 companies desperate to license her inventions? The answer lies in understanding that sometimes the most revolutionary innovations come not from high-tech laboratories but from real-world problems that demand practical solutions. Emma's story begins not with electric motors or battery packs, but with a family farm in crisis and a 15-year-old girl who refused to accept that there was nothing she could do about it. The Johnson family had been farming the same 800 acres in central Iowa for 4 generations. Emma's great-grandfather had purchased the land during the Great Depression, built it into a successful operation, and passed it down through a family that had agriculture in their blood. By all accounts, it should have been a thriving enterprise that could support another generation of Johnsons. But farming in the 21st century had become a battle of economics that was crushing family operations across the Midwest. Rising fuel costs, expensive machinery maintenance, environmental regulations, and unpredictable weather patterns had created financial pressures that made it increasingly difficult for smaller farms to remain profitable. We were spending more on diesel fuel and equipment repairs than we were making from crop sales, recalls Emma's father Mike Johnson, a third-generation farmer who had taken over the operation from his father. Every year it got harder to make the numbers work. We were facing the real possibility of losing the farm that had been in our family for over 70 years. The crisis came to a head during Emma's sophomore year of high school, when the family's main tractor, a 20-year-old diesel workhorse that was essential for planting, cultivation, and harvest, suffered a major engine failure that would cost more to repair than the machine was worth. Dad sat at the kitchen table with repair estimates and bank statements spread out in front of him, Emma recalls. I could see that he was trying to figure out how we could afford to replace our primary piece of equipment when we were already struggling to pay bills. The stress was affecting the whole family. Most 15-year-olds would have felt sympathy for their parents' difficulties, but would have assumed that complex agricultural and financial problems were beyond their ability to address. Emma had a different reaction. She started researching everything she could learn about tractor engines, agricultural equipment, and alternative power sources. What Emma discovered during her research changed everything. The diesel engines that powered conventional tractors were not only expensive to fuel and maintain, they were also remarkably inefficient for the types of tasks that farms actually needed. Most agricultural work involved relatively predictable power demands that could theoretically be met more efficiently by electric motors, if the right power management systems could be developed. I started wondering why tractors still use diesel engines when electric motors were more efficient, more reliable, and could provide better torque control, Emma explains. The more I researched, the more I realized that electric tractors could solve multiple problems that were hurting family farms. But Emma's research also revealed why major manufacturers hadn't successfully developed electric tractors for widespread agricultural use. The engineering challenges were significant. Electric tractors needed enormous battery capacity to work full days without recharging, sophisticated power management systems to handle varying loads, and designs that could withstand harsh agricultural environments while remaining affordable for family farms. Tesla had announced plans for electric agricultural vehicles, and several other companies were developing prototype electric tractors, but their solutions focused on high-end features and cutting-edge technology that would likely be too expensive for most farming operations. Emma realized that the industry was approaching electric agriculture from the wrong direction, trying to create premium products instead of practical solutions. Emma's approach would be completely different. Instead of starting with advanced technology and working toward agricultural applications, she would start with farming needs and work toward technological solutions. Instead of designing for impressive specifications, she would focus on solving the real problems that were affecting family farms like hers. The project began in the Johnson family's machine shop, a converted barn that Emma's grandfather had used for equipment repairs and modifications. The space was equipped with basic tools, welding equipment, and the accumulated mechanical knowledge of 3 generations of farmers who had learned to fix whatever broke rather than pay for expensive professional repairs. Emma's initial goal was modest: convert their broken diesel tractor to electric power using salvaged components in a limited budget. If successful, the conversion would save the family thousands of dollars in replacement costs while providing a more efficient and reliable machine for their farming operations. But Emma's ambitions expanded as she dove deeper into the engineering challenges. Her research had revealed not just how to convert existing tractors to electric power, but how to design electric agricultural machines that would be fundamentally superior to their diesel counterparts. Once I started understanding how electric motors could be optimized for agricultural work, I realized we had an opportunity to build something completely new, rather than just converting something old, Emma explains. Electric power could enable tractor designs that weren't possible with diesel engines, machines that were more efficient, more versatile, and better suited for the precision agriculture techniques that modern farming requires. Emma's design philosophy was shaped by her daily experience with farm work and her family's financial constraints. Every decision was evaluated based on practical utility and cost-effectiveness rather than technological sophistication or impressive specifications. The result was an approach to electric tractor design that prioritized real-world performance over laboratory metrics. Her first breakthrough came when she realized that agricultural work patterns were actually ideal for electric power management. Unlike highway driving, which requires sustained high-speed performance, farming involves periods of high-torque work alternated with lower power operations and natural breaks for field transitions. These usage patterns allowed for battery management strategies that could extend operating time far beyond what conventional electric vehicle approaches achieved. Emma designed a power system that used multiple smaller battery packs instead of single large batteries, with intelligent switching that could optimize power delivery based on immediate task requirements. During low-demand operations like field positioning, the system could operate on reduced power while charging reserve batteries. During high-demand operations like plowing, all batteries could deliver power simultaneously for maximum performance. But Emma's most innovative insight involved regenerative systems that could actually generate power during certain farming operations. Her design incorporated generators driven by ground engagement tools, allowing the tractor to harvest energy from field operations that would otherwise be wasted. Plowing, cultivating, and harvesting operations could actually charge the tractor's batteries while working. Emma realized that farming involves a lot of mechanical energy that conventional tractors waste, explains Dr. Robert Martinez, an agricultural engineering professor at Iowa State University who later studied Emma's designs. Her regenerative systems captured energy from field operations and converted it into electrical power. It was like having a tractor that partially powered itself while working. The engineering challenges were significant for someone with Emma's limited formal training and resources. Electric motor control systems required sophisticated electronics that were beyond her initial capabilities. Battery management demanded understanding of electrical engineering concepts that weren't covered in high school physics classes. Power integration needed mechanical engineering skills that typically required years of education and experience. Emma's solution was characteristic of her practical approach to complex problems. She learned what she needed to know, one challenge at a time, using online resources, community college courses, and guidance from anyone willing to share knowledge with a determined teenager. Her learning process was intensive and unconventional. Emma would spend hours after school watching YouTube videos about electric motor control, reading technical papers about battery management systems, and participating in online forums where professional engineers discussed power electronics. She took weekend courses at the local community college to learn welding, machining, and electrical installation techniques. Most remarkably, Emma began reaching out directly to engineers and researchers working on electric vehicle technology, asking questions about specific challenges she was facing with her tractor design. Many professionals were impressed by the sophistication of her questions and the practical applications she was pursuing. Emma would email me with questions about power inverter design or battery thermal management that showed she was working on genuine engineering problems, recalls Dr. Lisa Chen, an electric vehicle researcher at Stanford who became one of Emma's informal mentors. Her questions were practical and well-informed. It was clear that she was actually building something, not just learning about theoretical concepts. Emma's first prototype was completed during the summer between her sophomore and junior years of high school. The machine was built on the frame of the family's broken diesel tractor, but with entirely new electric drivetrain, power management and control systems that Emma had designed and assembled herself. The results of initial testing exceeded Emma's most optimistic expectations. Her electric tractor delivered more torque than the original diesel engine, operated much more quietly, required virtually no maintenance, and could work a full day on a single charge while actually gaining power during certain field operations through regenerative systems. But the most impressive performance metrics weren't the technical specifications, they were the practical advantages that directly addressed the problems facing family farms. Emma's electric tractor cost less than half as much to operate per hour as conventional diesel tractors, required minimal maintenance, and could perform precision agriculture techniques that were impossible with traditional machinery. Emma's tractor wasn't just electric, it was better, Mike Johnson explains. It could work longer, more quietly, and more efficiently than anything we had ever used. Most importantly, it was saving us thousands of dollars in operating costs that we desperately needed for other aspects of the farm operation. Word of Emma's success spread quickly through their farming community. Neighbors who had been skeptical about a teenager building farm equipment began asking for demonstrations and inquiring about whether Emma could convert their tractors to electric power. The first formal test of Emma's design came when she entered her electric tractor in the county fair's agricultural innovation competition. The judges, experienced farmers and equipment dealers who had seen decades of agricultural technology developments, were initially skeptical about a high school student's homemade electric tractor. Their skepticism disappeared during field demonstrations. Emma's tractor outperformed conventional machines in every practical test: pulling power, fuel efficiency, noise levels, emissions, and operating costs. More importantly, it demonstrated capabilities that diesel tractors simply couldn't match: variable speed control, instant torque delivery, and precision positioning that enabled agricultural techniques impossible with traditional equipment. Emma's tractor was genuinely revolutionary, recalls Judge Patricia Williams, a farm equipment dealer who had been selling agricultural machinery for over 30 years. It wasn't just a clever student project, it was a breakthrough that could change how farming is done. The performance advantages were undeniable. Emma's county fair victory attracted attention from agricultural publications, equipment manufacturers, and investors who had been searching for breakthrough technologies that could address the economic and environmental challenges facing modern agriculture. The first major media coverage came from Farm Progress, a leading agricultural publication that featured Emma's story as an example of innovation emerging from practical farming needs rather than corporate research laboratories. The article generated responses from farmers across the country who were interested in electric tractor technology and manufacturers who wanted to understand how a teenager had achieved breakthroughs that had eluded their engineering teams. But the attention that really changed Emma's trajectory came from Tesla's agricultural division, which had been developing their own electric tractor designs for eventual commercial production. Tesla engineers who read about Emma's work were intrigued by her power management innovations and regenerative systems that their own designs hadn't incorporated. Dr. Michael Park, Tesla's head of agricultural vehicle development, contacted Emma's family to request a meeting and demonstration of her electric tractor technology. What was initially planned as a brief consultation evolved into a detailed technical evaluation that left Tesla's engineering team impressed and concerned about their own development timeline. Emma had solved problems that our team was still working on, Dr. Park later explained. Her power management system was more efficient than ours, her regenerative capabilities were more advanced, and her overall approach to agricultural electric vehicle design was more practical than what we had developed after 2 years of engineering work with unlimited resources. Tesla's interest in Emma's work led to discussions about potential licensing agreements, collaborative development opportunities, and consulting arrangements that could benefit both parties. But Emma's response to Tesla's overtures revealed the depth of her commitment to helping family farms, rather than simply creating impressive technology. Tesla wanted to license my designs for their premium electric tractors that would cost $200,000 or more, Emma explains. But my goal was always to create affordable solutions that could help farms like ours survive economically. Licensing my technology for expensive luxury tractors wouldn't solve the problems I was trying to address. Emma's decision to decline Tesla's initial licensing offer was based on her recognition that her technology's greatest value lay in its potential to democratize advanced agricultural capabilities rather than enhance premium products for wealthy farming operations. Instead of partnering with Tesla, Emma decided to develop her technology independently, with the goal of creating affordable electric tractors that could be accessible to family farms facing economic pressures, similar to what her own family had experienced. This decision required Emma to transition from individual inventor to entrepreneur, a challenge that would test her business abilities as thoroughly as her engineering skills had been tested during the tractor's development. Emma's business approach reflected the same practical philosophy that had guided her engineering work. Instead of seeking venture capital funding or corporate partnerships that might compromise her mission of affordability and accessibility, she decided to bootstrap her company using profits from custom electric tractor conversions and consulting services. Johnson Electric Agriculture was officially founded during Emma's junior year of high school, operating out of the family's machine shop with Emma serving as chief engineer, her father managing operations and her mother handling business administration. The company's initial services included electric tractor conversions, custom power system installations, and consulting on agricultural electrification projects. The demand for Emma's services exceeded their capacity to deliver almost immediately. Farmers from across the Midwest were requesting electric tractor conversions, agricultural equipment manufacturers were seeking consulting on electric vehicle development, and investment firms were offering funding for expansion. Emma's approach to managing this growth demonstrated business wisdom that impressed experienced entrepreneurs and investors. Rather than expanding rapidly to meet immediate demand, she focused on perfecting her designs, training additional technicians, and building sustainable business processes that could maintain quality while serving more customers. Emma understood that her reputation was built on delivering solutions that actually worked for farming families, explains Dr. Sarah Rodriguez, a business professor at the University of Iowa, who studied Emma's entrepreneurial approach. She prioritized customer success over rapid growth, which created a foundation for long-term business success. Emma's junior year of high school was consumed by balancing academic requirements with the demands of running a growing technology business. Her daily schedule included attending classes, completing homework, managing engineering projects, and handling business operations that were generating significant revenue. The challenge was complicated by media attention that continued to grow as Emma's story attracted national coverage. Agricultural publications, business magazines, and technology blogs all featured articles about the teenager who had created electric tractor technology that outperformed corporate development efforts. Emma's response to media attention reflected her focus on practical results rather than personal recognition. She used interviews and publicity opportunities to educate people about the potential for electric agriculture and the importance of supporting family farming operations, rather than promoting herself or her company. Emma never sought publicity for its own sake, recalls Jennifer Walsh, a journalist who covered Emma's story for several national publications. She saw media attention as an opportunity to advance conversations about agricultural innovation and rural economic development. Her focus was always on the bigger picture rather than personal celebrity. This principled approach to business development and public relations created credibility with customers, industry professionals, and potential partners who recognized that Emma's motivations were aligned with practical problem-solving rather than personal enrichment. By the end of her junior year, Johnson Electric Agriculture had completed over 50 tractor conversions, consulted on agricultural electrification projects in 12 states, and generated revenue that exceeded what most small technology companies achieved in their first several years of operation. But Emma's most significant achievement during this period was completing the design and prototype testing of her second-generation electric tractor, a machine built from scratch rather than converted from existing equipment, incorporating 2 years of field experience and customer feedback into a design optimized specifically for electric agricultural applications. The new tractor represented a comprehensive rethinking of agricultural machinery design based on the unique capabilities and advantages that electric power could provide. Instead of simply replacing diesel engines with electric motors, Emma had reimagined how tractors could be designed when freed from the constraints of traditional powertrains. Her second-generation design featured modular construction that allowed farmers to configure tractors for specific applications, advanced autonomous capabilities that could reduce labor costs and improve precision, and integrated data collection systems that provided valuable information for crop management and operational optimization. Emma's second-generation tractor wasn't just electric, it was intelligent, explains Dr. Martinez, who evaluated the design for potential agricultural applications. It incorporated sensors, data processing, and autonomous capabilities that could revolutionize how farming is done. The machine could learn from farming operations and optimize its own performance based on field conditions and crop requirements. The performance capabilities of Emma's new design exceeded even Tesla's projected specifications for their planned agricultural vehicles. Her tractor delivered more power, longer operating time, more advanced autonomous features, and better data integration, all at a projected manufacturing cost that was less than half of Tesla's anticipated pricing. Field testing during the summer before Emma's senior year confirmed that her design advances translated into practical advantages for farming operations. The new electric tractor could perform complex agricultural tasks with precision and efficiency that surpassed conventional equipment while providing data insights that enabled better crop management decisions. Emma's success with her second-generation design attracted attention from agricultural equipment manufacturers who recognized that her technology represented a genuine breakthrough in farm machinery capabilities. John Deere, Case IH, and several other major manufacturers approached Emma about potential acquisition, licensing, or partnership opportunities. But Emma's response to corporate interest remained consistent with her original mission of supporting family farming operations. She was willing to consider partnerships that would make her technology more widely available at affordable prices, but she wasn't interested in deals that would simply enhance existing premium product lines. Emma had created something genuinely revolutionary, and every major manufacturer wanted access to her technology, explains Dr. Park, who continued following Emma's work after Tesla's initial discussions, but she had clear principles about how her innovations should be used, and she wouldn't compromise those principles even when offered significant financial incentives. Emma's senior year of high school was dominated by decisions about her future that would have challenged most adult entrepreneurs. She had created technology that could generate significant wealth through corporate partnerships, but she was also committed to a mission that might require sacrificing immediate financial opportunities for longer-term social impact. The decision was complicated by college acceptance letters from engineering programs at MIT, Stanford, and other prestigious universities that had learned about Emma's work and were eager to have her as a student. Academic success had always been important to the Johnson family, and Emma's parents were concerned about whether focusing on business development might compromise her educational opportunities. Emma's solution to these competing priorities reflected the same systematic approach she had applied to engineering and business challenges. She developed a plan that would allow her to pursue university education while maintaining control of her company's direction and ensuring that her technology remained aligned with her original mission. She accepted admission to MIT's mechanical engineering program with arrangements to complete coursework on an accelerated schedule that would accommodate her business responsibilities. She also established a trust structure for Johnson Electric Agriculture that would preserve the company's mission of affordable agricultural innovation while providing management flexibility during her university years. Emma had created a genuine dilemma for herself, reflects her father, Mike Johnson. She had opportunities that any entrepreneur would envy, but she also had principles that were more important to her than financial success. Her solution was characteristically thoughtful and practical. Emma's approach to managing her transition from high school inventor to university student and established entrepreneur became a case study in balancing personal development with business responsibilities. Her ability to maintain focus on long-term goals while managing immediate demands impressed business advisors and academic mentors who worked with her during this transition. The summer before college marked another major milestone in Emma's story, the first commercial production of Johnson Electric agriculture tractors built entirely to Emma's specifications, rather than converted from existing machines. The production launch was deliberately small-scale, with an initial run of 25 tractors that would be sold directly to farming operations that had been involved in field testing and development feedback. Emma's goal was to validate manufacturing processes and gather real-world performance data before expanding production to larger scales. The commercial launch attracted significant media attention, with agricultural publications and business magazines covering the story of a teenager whose technology had evolved from a high school project to a commercial product that was competing with established manufacturers. More importantly, the launch demonstrated that Emma's technology worked effectively in diverse agricultural applications and operating conditions. Farmers who purchased the initial production tractors reported performance results that confirmed the advantages Emma had predicted: lower operating costs, higher precision, better reliability, and enhanced productivity compared to conventional equipment. Emma's tractor performed exactly as promised, reports David Chen, an Iowa corn farmer who purchased one of the first commercial units. It saved us money on fuel and maintenance while providing capabilities that our diesel tractors couldn't match. Most importantly, it proved that a small farming operation could afford advanced technology that was previously only available to large agricultural corporations. The success of Emma's commercial launch coincided with major developments in the broader agricultural industry that validated her strategic approach to electric farm equipment. Rising fuel costs, tightening environmental regulations, and increasing labor costs were creating economic pressures that made electric agricultural equipment increasingly attractive to farming operations of all sizes. Tesla finally announced their own electric tractor specifications during Emma's senior year, with projected performance capabilities that were impressive but fell short of what Emma had already achieved in commercial production. More significantly, Tesla's pricing was projected to be nearly 3 times higher than Emma's commercial tractors, confirming her analysis that major manufacturers were focusing on premium markets rather than accessible solutions. Emma had correctly predicted that the agricultural market needed affordable electric solutions rather than premium technology showcases, observes Dr. Rodriguez, who continued studying Emma's business strategy development. Her focus on practical value and economic accessibility positioned her perfectly for market conditions that were developing throughout the agricultural industry. Emma's freshman year at MIT was complicated by the demands of managing a growing company while adapting to university academic requirements. Her engineering coursework was challenging despite her practical experience, and her business responsibilities required attention that competed with study time and social opportunities that were important for college development. But Emma's university experience also provided opportunities to expand her technical knowledge and develop professional relationships that enhanced her ability to advance her technology and business goals. MIT's engineering faculty and resources offered capabilities that could accelerate her research and development work beyond what was possible with her previous self-directed learning approach. Dr. Jennifer Kim, Emma's faculty advisor in mechanical engineering, describes Emma's impact on MIT's academic environment. Emma brought real-world engineering experience that enhanced classroom discussions and laboratory work. She had solved problems that many students only encounter in theoretical contexts, and her practical insights helped everyone understand how engineering principles apply to actual technical challenges. Emma's sophomore year at MIT marked another breakthrough in her technology development, the integration of artificial intelligence and machine learning capabilities that could optimize tractor performance based on field conditions, crop requirements, and farming practices specific to individual operations. This advancement represented a fundamental evolution in agricultural machinery, from simple mechanical tools to intelligent systems that could learn from farming operations and continuously improve their effectiveness. Emma's AI-enhanced tractors could adjust power delivery, optimize field patterns, and coordinate multiple farming tasks in ways that maximized crop yields while minimizing resource consumption. Emma's integration of AI into agricultural machinery was genuinely revolutionary, explains Dr. Lisa Park, an MIT professor who collaborated with Emma on machine learning applications. She created systems that could learn from farming operations and become more effective over time. It was like having agricultural equipment that got smarter with experience. The AI capabilities also enabled Emma's tractors to collect and analyze agricultural data that provided valuable insights for crop management, soil health, and operational efficiency. Farmers using Emma's equipment gained access to information that had previously been available only to large agricultural operations with dedicated research resources. Emma's junior year at MIT coincided with major expansion of Johnson Electric Agriculture's manufacturing and distribution capabilities. Demand for her tractors had grown beyond what small-scale production could satisfy, requiring investments in manufacturing facilities, supply chain development, and quality control systems. The expansion was funded through a combination of business profits, strategic partnerships with component suppliers, and a carefully structured investment round that provided capital while preserving Emma's control over the company's mission and direction. Emma had created a business that was genuinely profitable and growing rapidly, but she maintained her principles about affordability and accessibility throughout the expansion process, explains Dr. Martinez, who served as a business advisor during this period. She proved that social mission and commercial success could be compatible when business strategy was aligned with genuine market needs. By her senior year at MIT, Emma's technology had evolved into a comprehensive platform for electric agricultural equipment that included tractors, harvesters, and specialized implements designed specifically for electric power applications. Johnson Electric Agriculture had become a significant player in the agricultural equipment industry, with products sold throughout the United States and international markets. Emma's senior capstone project at MIT focused on developing autonomous farming systems that could integrate multiple electric machines into coordinated operations requiring minimal human supervision. The project represented the convergence of her practical farming experience, engineering education, and business development work into a comprehensive vision for the future of agriculture. The autonomous farming system demonstrated during Emma's senior presentation could plant, cultivate, and harvest crops with precision and efficiency that exceeded human-operated equipment, while providing detailed data about crop conditions, soil health, and resource utilization that enabled better farming decisions. Emma's senior project represented a complete reimagining of how farming could be done, recalls Dr. Kim, who supervised the work. She had created systems that could transform agriculture from labor-intensive operations to data-driven processes that maximize both productivity and sustainability. Emma's graduation from MIT coincided with Johnson Electric Agriculture's achievement of a major milestone. Their electric tractors had collectively operated over 1 million field hours, demonstrating reliability and performance that established electric agriculture as a viable alternative to conventional farming equipment. The company's success had also created economic benefits that extended beyond individual farming operations. Emma's manufacturing facilities had created jobs in rural communities, her supply chain partnerships had generated business for local suppliers, and her focus on affordable technology had helped family farms remain economically viable in an increasingly challenging agricultural economy. Emma's success demonstrated that innovation could create value for entire communities rather than just individual inventors, observes Dr. Rodriguez, who studied the broader economic impacts of Emma's work. Her company created a model for how technology development could support rural economic development while addressing practical problems facing agricultural communities. Today, at 22 years old, Emma Johnson leads a company that has revolutionized agricultural equipment and established new standards for electric farming technology. Her tractors are used on farms throughout the world. Her innovations have been adopted by major manufacturers, and her business approach has become a case study for mission-driven entrepreneurship. But Emma's greatest achievement may be her demonstration that breakthrough innovations can emerge from practical problem-solving rather than theoretical research, and that young people can create solutions to complex challenges when they combine technical knowledge with genuine understanding of real-world problems. Tesla eventually abandoned their agricultural vehicle development program, acknowledging that Emma's technology and business approach had established market conditions that made their premium-focused strategy unviable. Other major manufacturers have licensed Emma's innovations or developed competing products based on principles she pioneered. Emma's story continues to inspire young inventors, agricultural communities, and entrepreneurs who recognize that meaningful innovation often comes from understanding problems deeply rather than pursuing technology for its own sake. Her journey from farm crisis to industry leadership demonstrates that age, resources, and formal credentials are less important than creativity, determination, and genuine commitment to solving important problems. Emma showed us that the most important innovations often come from people who understand problems firsthand, rather than those who study them from a distance, reflects Dr. Park, who now teaches courses on agricultural innovation that use Emma's work as a primary example. Her success came from combining technical capability with genuine empathy for the people whose problems she was trying to solve. The 16-year-old who started building an electric tractor to save her family's farm became a young woman whose innovations transformed an entire industry, while proving that breakthrough solutions often emerge from the most unexpected places when they're guided by genuine purpose and practical wisdom. Emma Johnson's legacy extends far beyond agricultural technology, to include fundamental insights about innovation, entrepreneurship, and the relationship between technical capability and social impact. Her story reminds us that the most powerful innovations are often those that solve real problems for real people, rather than those that simply demonstrate impressive technology. Her journey from desperate teenager to industry leader proves that extraordinary achievements are possible when creativity, determination, and genuine care for others combine to address challenges that matter to communities and families whose needs might otherwise be overlooked by established institutions and corporations. The girl who refused to accept that her family's farm couldn't survive became a woman who ensured that thousands of farming families could thrive through access to technology that made their operations more efficient, profitable, and sustainable. Emma's story continues to unfold as she develops new technologies, expands her business impact, and mentors other young inventors who are inspired by her example to pursue their own solutions to important problems. Her legacy is written not just in patent filings and business metrics, but in the farming communities that remain viable because a teenager was willing to imagine that things could be different and had the determination to make that imagination reality.